Welcome back to linear algebra. In this video, we're going to be taking a look at symmetric matrices. Earlier in the course, I mentioned the idea of the matrix transpose operation and how we could use that to define the idea of a similar matrix. At the time, I mentioned that our textbook went through a number of properties of the matrix transpose and the symmetric matrices that I didn't want to talk about then because it would be several weeks before any of it was useful, just enough time for you to completely forget everything we had talked about. We've now reached the point where it's going to be useful, so let me get my head out of the way and let's start talking a little bit about the transpose of a matrix, which again, I have defined before, but it's been a while. So if we define matrix A So we have matrix A here is an m by n matrix, and we have all of the entries listed out, indexed. The transpose of A is going to be the matrix that swaps row and column. And the transpose of an m by n matrix, by its definition, will be an n by m matrix. And we've got a couple of things that we can do with the matrix transpose. If instead of talking about a matrix in terms of its individual elements, if we have a matrix which is defined by a sequence of column vectors, then the transpose of that matrix will be a sequence of row vectors. So the transpose of a column vector will be a row vector. The transpose of a row vector will be a column vector. So if we have column vector U1, row vector U1 transposes the same elements, just written across instead of written down. So we can take a row vector matrix described using column vectors and turn it into a matrix described using row vectors. We can actually use the same process to take a matrix described using row vectors and turn it into a matrix described using column vectors. Because one of the most simple but important properties of the matrix transpose operation is that if you take the transpose of a matrix, you come back to the matrix where you started. I think that's straightforward enough. I'm not going to try to prove it. Instead, I want to go on to prove something a little bit more challenging and also incredibly important. let's take two matrices, A and B, and we want to make sure that we have these matrices set up in such a way that the product A times B is defined. Remember that the product of two matrices is defined if and only if the number of columns in the first matrix is equal to the number of rows in the second matrix. Otherwise, the matrix multiplication is not defined. And if we have that defined, our claim is that if we want to take the transpose of the product, we could take the transpose of each of the factors and multiply them in the opposite order. In order to prove that this works, I want to be able to write out matrix A as a sequence of row vectors and matrix B as a sequence of column vectors. And of course, using the definition of matrix multiplication, you take each row of matrix A and dot it with the vectors that are the columns of matrix B. So we get A1.B1, we get A1.B2. Sorry, I get so used to n's. Let's assume we have m rows in matrix A and n columns in matrix B. I forgot what I was doing and left the same variable for both, which is definitely not what we want. They don't have to be the same size. And then we get down to A1, Bn, all right, so we can multiply two matrices. That's nothing too out of the ordinary. But our goal was not to multiply two matrices. Our goal was to take the transpose of multiplying two matrices. So let's take the transpose of this matrix. Again, just takes the columns of the first matrix and turns them into the rows of the new matrix. Or alternately takes the rows of the first matrix and turns them into the columns of the new matrix. Right. So having that at our disposal will be convenient later on in this proof. But instead of continuing with that, I want to break and take a look at the other side of the equation we're trying to prove, B transpose A transpose. The transpose of a matrix defined by column vectors gives you row vectors, and the transpose of a matrix defined by row vectors gives you column vectors. So we end up with a matrix which is defined by row vectors, B1, B2, down to Bn, multiplied by a matrix defined by column vectors, A1, A2, over 2, AM. And I'm not going to worry about distinguishing that these are all the transposes because we had A's originally defined as row vectors, B's originally defined as column vectors. As far as the Euclidean vectors are concerned, it's the same thing. It's just two different notations for the same vector. But we can do the same thing here that we did previously. To multiply two matrices, you dot the row of the first matrix with the column of the second one. So this is B1 dot A1. This is B1 dot A2, and we keep going until we get B1 dot with AM. Then we take the second row, B2, and we dot it with A1. We take B2 and we dot it with A2, and we keep going until we dot B2 with AM. We do that for the third row and the fourth row till we get down to the nth row. And very surprising, I'm sure, this looks incredibly familiar to us. Still on the screen conveniently. AB transpose had A1.B1, A2.B1. B transpose A transpose has B1.A1, B1.A2, and so on like that. So the last thing we need to know is that the Euclidean dot product is commutative. I'm not going to take the time to rewrite this matrix with everything flipped over. You will get exactly the same thing for B transpose A transpose that we got when we took AB and transposed that whole thing. Another thing, I'm going to call it a theorem, although it shouldn't take that much work. It's kind of the definition. If we take two vectors u and v and think about the Euclidean dot product, that is by its very definition the same thing as taking the row vector, and for convenience we'll write v as a row vector here, and we'll leave u as a column vector, and you'll see why that's useful in the next theorem. But again, the definition of the matrix multiplication is the Euclidean dot product. And so the transpose of a column vector is a row vector. We have a matrix that is one row and columns times a matrix that is one column and rows. And you multiply everything together, you get a single entry left, which is the value of that dot product. But that makes a lot of sense, at least I hope, and is going to be a very important part of our reasoning for the theorem. Let's let our vectors u and v be in Rn still. And let's take A as an n by n matrix, a matrix transformed from Rn to Rn. And our claim here is that if we multiply matrix A times U and then dot with V, that's the same thing as taking U dot, the product of A transpose times V. And the proof here is a fairly straightforward algebraic proof using the properties of the dot product and the transpose of product of matrices that we've just proven. If we start with A times U dot V, that's the same thing as V transpose times AU. And matrix multiplication is associative, so we could take V transpose times A and then multiply by U. Now V transpose times A, since we're looking at a product and there's a transpose involved, it hopefully will make sense to kind of work backwards on the theorem of transpose of a product. So it's listed backwards of how we proved it, but if you have A transpose times V transpose transpose and you want to take the transpose of the whole thing, well, then you would undo taking the transpose, I guess, here and switch the order of multiplication. And of course, V transpose transpose is just V. And finally, vector transpose times another vector is one of the forms we can use to describe the dot product. Getting us exactly where we said we wanted to get to. Nothing too outlandish here in our discussion of the matrix transpose, but a couple of properties that are going to be very useful to us in the next couple of lessons. Before we wrap up here, I said that this lesson was on symmetric matrices. So far, we have talked about the transpose of a matrix, which is important, but not quite the same thing as a symmetric matrix. So let's let A be any symmetric matrix. I'm sorry, let's let A be any square matrix. And technically, we could define this for any matrix at all, but it doesn't take much thought to realize that only a square matrix can be symmetric. Because a matrix is symmetric if it is equal to its transpose. And for an M by N matrix, the transpose is an N by M matrix. Two matrices cannot be equal unless they have the same dimensions. So the only way that this can work is if M and N happen to be the same value, if A is a square matrix. And there are going to be plenty of things we can do with symmetric matrices in the coming lessons. One of my favorite has to do with orthogonal vectors and eigenspaces, the things we've been talking about recently. So let's let A be a symmetric matrix. Then eigenvectors from different eigenspaces are orthogonal. Again, assuming the Euclidean vector spaces and the Euclidean dot product. And the proof here is fairly ingenious, I think. All right, so we're talking about eigenvectors from two different eigenspaces. So to have different eigenspaces, we need different eigenvalues. Let lambda 1 and lambda 2 be distinct eigenvalues of A. And let's take U1 to be one of the eigenvectors from the eigenspace of lambda 1. And let's let U2 be one of the eigenvectors from the eigenspace of lambda 2. And the theorem says that these vectors will be orthogonal. Orthogonal vectors have a dot product of 0, so we want to show that U1 dot with U2 is equal to 0. And in order to do that, well, the only thing we know about U1 and U2 is that they are eigenvectors from matrix A. So A times U1 is equal to lambda 1 U1, and A times U2 is equal to lambda 2 U2. By the definition of an eigenvector. And then the other thing we have to work with is that A is symmetric. Because of that, we're going to want to somehow in this process involve the matrix transpose operation. Based on the theorems we've just proven, it's hopefully not too much of a surprise to you that we're going to do that by considering AU1 dot with U2. We just proved the theorem about the dot product. AU1 dot with U2 is the same thing as U1 dot with A transpose times U2. And because A is symmetric, A transpose is the same thing as A. So we have that AU1 dot with U2 is the same thing as U1 dot with A times U2. And this will be true for any symmetric matrix A. Now from here, because U1 and U2 are eigenvectors, we have that lambda 1 U1 dot with U2 is equal to U1 dot with lambda 2 U2. And in the Euclidean dot product, and really in any inner product, you can pull out constant factors. So this is lambda 1 times U1 dot U2 is equal to lambda 2 times U1 dot with U2. And rearranging the equation a little bit, lambda 1 U1 dot with U2 minus lambda 2 U1 dot with U2 must be equal to 0. And factoring, this gives me that lambda 1 minus lambda 2 times U1 dot with U2 is equal to the 0. And that's basically it. Right? Just playing around with the theorems we just proved, a little bit of algebraic manipulation, basic algebra on real numbers stuff. And then we can use the zero product rule. We have two things multiplied together whose result is 0. So either the first thing is equal to 0, or the second thing is equal to 0. If lambda 1 minus lambda 2 is equal to 0, that means that lambda 1 is equal to lambda 2. But we know that that's not true because lambda 1 and lambda 2, we assumed at the beginning, were two distinct eigenvalues. We needed to have eigenvectors from two different eigenspaces, so we needed those eigenvalues to be different. And because that is not an option, the only thing left is that U1 dot U2 is equal to 0. That's what it takes to be orthogonal. And that gives us our result. All right. So with that, I'm going to wrap up this video. Next time, I'm going to take a look at symmetric matrices. I'm going to take a look at orthogonal vectors and build up a couple of new ideas related to that. Take a look at the practice problems related to these topics, and I'll see you in the next video.